What's going on, guys? Justin here, and welcome back to our 20th example video following our course on proof writing. Now, today's example video is going to be on limit proofs, specifically using the epsilon-delta definition of the limit. So let me go ahead and write out that definition for you, and then we can use it to get into this first example. Okay, so I've written out the epsilon-delta definition for evaluating a limit here. So suppose we have a function from x to r, where x is a subset of r, and we have an element a in x. We see that the limit evaluated as x goes to a of f of x is equal to L if for all epsilon greater than 0, there exists a delta greater than 0 such that the absolute value of x minus a is less than delta, implies that the absolute value of f of x minus L is less than epsilon. So basically, in order to do this type of proof, we are trying to find our specific delta. So we usually start from the back and work to the front. So we're going to do some scratch work for that, like you've seen in previous proofs. So for scratch work, we're going to suppose that we have our f of x minus L condition there. So we're going to look at the absolute value of, in this case, we have 5x minus 7. And then that's going to be minus the limit, which is just 3, and that is less than epsilon. And we want to work to x minus a is less than something, and that's what we are going to set to be our delta. So from here, let's go ahead and combine our minus 3 and minus 7 here. So we're going to get the absolute value of 5x minus 10 is less than epsilon. And we can see that we can factor out a 5 from our absolute value there, as the absolute value of 5 is just 5. And we'll have 5 times the absolute value of x minus 2. And that should ring some bells in your head, as that's exactly what we want to be in our absolute value, because we have the limit as x goes to 2. So we're looking for something of the form the absolute value of x minus 2. So we have 5 times the absolute value of x minus 2 is less than epsilon. And now all we need to do is divide that 5 over. So when we do that, we will get that the absolute value of x minus 2 is less than epsilon over 5. And this epsilon over 5 is what we are going to set to be our delta. So let me go ahead and draw an arrow and write delta there. So now we can actually begin our proof since our scratch work is done. So we're going to start the proof like this. So given epsilon greater than 0, we're going to take our delta to be what we just derived right there. Delta is going to be epsilon over 5. And then we are going to suppose that we have the absolute value of x minus 2 is less than delta, which is of course equal to epsilon over 5. But we can see we can multiply our 5 right back over, and we will get 5 times the absolute value of x minus 2 is less than epsilon. And we want to show that the absolute value of f of x minus L is less than epsilon, so we want to manipulate this to do that. And we're kind of just undoing our steps from our scratch work here, so we're going to multiply that 5 inside, and we'll get the absolute value of 5x minus 10 is less than epsilon, but we can see we are almost done. All we need to do is rewrite the inside of our absolute value there, and we will have what we want. We can rewrite that as 5x minus 7 minus 3 is less than epsilon. And that's all we need to do to finish this proof. As we started with an arbitrarily small epsilon and took a specific delta that let us show that the absolute value of x minus a is less than delta, implies that the absolute value of f of x minus L is less than epsilon. Great, so let's go ahead and get into our second proof like this. Great, so for this limit, we have the limit as x goes to negative 3 of x squared minus 2 is equal to 7. So I'm not going to write out the precise definition of the limit again, but I am going to start with our scratch work like we did on the last one. So for our scratch, we will have the absolute value of x squared minus 2 minus 7 is less than epsilon. And we can see that we can combine that negative 7 and negative 2, and then we will get the absolute value of x squared minus 9 is less than epsilon. And now we want to factor this x squared minus 9, so we will get the absolute value of x minus 3 times the absolute value of x plus 3 is less than epsilon. And so we're going to want to do a little wishful thinking here. So we're going to look at if the absolute value of x minus 3 is less than 1. Well, we can use our definition of absolute value to see that that will then mean that we have that x minus 3 is between -1 and 1. But we can add 3 to both sides there, and we will get a new inequality, which will be 2 is strictly less than x, which is strictly greater than 4. And we want to manipulate this to get an inequality for x plus 3. That means we can add 3 to this inequality, and we will get that 5 is strictly less than x plus 3, which is strictly less than 7. And so that means we can obtain the following strict inequality for the absolute value of x plus 3. We will have the absolute value of x plus 3 is strictly less than 7. That means we will have no problem if we substitute a 7 in for our inequality up here in place of our absolute value of x plus 3. So we can go ahead and make that substitution. We will have that the absolute value of x minus 3 times 7 is less than epsilon. And we can divide by 7 to arrive at our new epsilon, which we will choose to be our delta. So we will have the absolute value of x minus 3 is strictly less than epsilon over 7, which, like last time, we will choose to be our delta. But we will need this extra condition on our delta that it is less than 1 from our wishful thinking from before. Let's go ahead and jump into the formulation of the actual proof now that our scratch work has been completed. So just like the last proof, we are going to begin with given epsilon greater than 0. And we're going to take our delta to be the minimum of the following two. So it's going to be the minimum of 1 and epsilon over 7. And so we only have to add in our minimality there because of our wishful thinking at the top. Otherwise, we could just take our delta to be epsilon over 7. So then we're going to suppose that we have the absolute value of x minus 3 is strictly less than delta. And so by our minimality condition, we can break this up into two different statements that will both be true. That means we have the absolute value of x minus 3 is strictly less than 1, and that the absolute value of x minus 3 is strictly less than epsilon over 7, as it is less than the smaller of the two, so then it must be less than the other one as well. But now we want to demonstrate our calculation that we did earlier to get our 7. So we can split up our absolute value there to get 2 is strictly less than x, which is strictly less than 4, which of course implies that 5 is less than x plus 3, which is less than 7. And here we have demonstrated that we can bound our absolute value of x plus 3 above by 7 for our proof here. And then we want to observe our fact that we used when we factored our f of x. So we want to observe that the absolute value of x squared minus 9 is equal to the absolute value of x plus 3 times the absolute value of x minus 3. But we can see we can make two substitutions here. We know that the absolute value of x minus 3 is strictly less than epsilon over 7, and we use the fact that x minus 3 is less than 1 to show that the absolute value of x plus 3 is strictly less than 7. So we can make two substitutions here. So we'll have that the absolute value of x plus 3 times the absolute value of x minus 3 must be strictly less than 7 times epsilon over 7. But we can see that those two epsilons will cancel, and we will get that the absolute value of x plus 3 times x minus 3 is strictly less than epsilon. But remember that the absolute value of x plus 3 times x minus 3 is equal to the absolute value of x squared minus 9. But the absolute value of x squared minus 9 is exactly what we want to show is less than epsilon. It is equal to the absolute value of x squared minus 2 minus 7, which is of course less than epsilon, which completes our proof as we have from the top our f of x minus our limit L is less than epsilon. Great, so let's go ahead and get into our next proof. So for this proof, we want to show that the limit as x goes to 4 of 1 over x minus 2 is equal to 1/2. So once again, we are going to start out with some scratch work here. And we want to manipulate this to get the absolute value of x minus 4 is less than something, which we will define to be our delta. So we might want to start by clearing our denominators, but first let me write out our function here. So we'll have 1 over x minus 2, and then minus 1/2 is less than epsilon. So let's clear these denominators first. I'm going to multiply by 2 times x minus 2, or just 2x minus 4 on both sides there. And so when we multiply that in on our left-hand side, we will get the absolute value of, well, that top part, well, that left term will just be a 2. And then we will get minus x minus 2 within our absolute value there. And then on our right-hand side, we will get epsilon times the absolute value of 2x minus 4. And I think I said we were going to multiply by 2x minus 4, but to be careful, we are going to multiply by the absolute value of 2x minus 4. So we can see that we can combine our 2's on our left-hand side here, and we will get 4 minus x, but you can flip the signs within the absolute value as long as you change them both. So we're going to change that to x minus 4 because that is of the form that we desire. So this will become x minus 4 here, and that is going to be less than epsilon times the absolute value of 2x minus 4. Great. And so once again, we are going to want to do some wishful thinking here so that we can bound our 2x minus 4. Now, in the last example, we had the problematic term on the left-hand side, or in the numerator of our left-hand side, but this time it's on our right-hand side, which would theoretically be in the denominator of our left-hand side. So we're going to need to bound our 2x minus 4 below instead of above this time. So let's go ahead and use wishful thinking and see what we can get, see where we can push this absolute value of x minus 4. So once again, we are going to consider if the absolute value of x minus 4 is strictly less than 1. And we're going to use the definition of the absolute value of x minus 4 to split this up into the following inequality, where we have 3 is less than x, which is less than 5. And then we can manipulate this to get to 2x minus 4, so we can multiply by 2 there. And we will get 6 is less than 2x, which is less than 10. And now all that's left to do is subtract by 4 and rewrite our absolute value. So let's go ahead and subtract by 4 first. And we will get 2 is less than 2x minus 4, which is less than 6. Now rewriting that as an absolute value and reminding you that we want to bound this absolute value of 2x minus 4 below, we will get that we have the absolute value of 2x minus 4 is strictly greater than 2. And that means we can pick the following for our delta. We will have the absolute value of x minus 4 is less than epsilon, and then we have this 2 for our absolute value of 2x minus 4, so it'll be epsilon times 2, or 2 epsilon. So let's take this epsilon to be our delta, reminding you that this delta will need to be less than 1. And we're going to accomplish that by taking a minimum of our delta, which we did on the last problem. So once again, we're going to start our proof just the same way we've been starting all of these proofs, given epsilon greater than 0. So given epsilon greater than 0, we are going to take our delta to be, like I said earlier, delta is going to be the minimum of 1 and our 2 epsilon that we have chosen above here. So from here, we are going to suppose that we have the absolute value of x minus 4 is less than delta, which we can split up into the following 2 statements. So that implies that the absolute value of x minus 4 is less than 1, and the absolute value of x minus 4 is less than 2 epsilon. But we know from our prior calculation that we can manipulate this absolute value of x minus 4 is less than 1 to get our absolute value of 2x minus 4 is greater than 2. So I'm just going to write that down because we've already done the calculation. So the absolute value of x minus 4 is less than 1 implies that the absolute value of 2x minus 4 is greater than 2. And like I said, we've already done the calculation for that, so this isn't a stretch. And so from here, we want to use all of these facts that we have established to show that the absolute value of x minus 4 is less than epsilon. So we want to observe the following. We have that 2 epsilon is greater than or equal to delta, as delta is the minimum, so it could be equal to it or it could be less than it. And we know that the absolute value of x minus 4 is strictly less than delta, which we have supposed above. And we also know from our prior calculation that the absolute value of x minus 4 is equal to 1 over x minus 2 minus 1/2 times the absolute value of 2x minus 4, which is strictly greater than 2 times the absolute value of x minus 4. And we can see that that then implies that the absolute value of x minus 4 is strictly less than epsilon, which completes our proof. So now we're going to get into the proofs of 2 really important theorems. So for this first proof, we are going to be proving that limits are unique. So if we have the limit as x goes to a of f of x, and we get two different limits, L and M. We want to show that L is equal to M. And we're going to do this using the precise definition of the limit. So we're going to begin by supposing that the limit as x goes to a of f of x is equal to L, and that the limit as x goes to a of f of x is equal to M as well. Well, we know by using our precise definition of the limit that we have the following. So then for all epsilon greater than 0, there exists we'll call delta 1 and delta 2 that are both greater than 0, such that the following holds true. We have the absolute value of x minus a is less than delta 1, and that implies that the absolute value of f of x minus L is less than epsilon over 2, and we'll have that the absolute value of x minus a is less than delta 2, which implies that the absolute value of f of x minus m is also strictly less than epsilon over 2. And I've set them to epsilon over 2 so that they will add up to make a nice pretty epsilon at the end of the proof. But remember that epsilon is arbitrarily small, so how we represent it does not particularly matter. So from here, we are going to let our delta equal the minimum of our delta 1 and delta 2. So delta is equal to the minimum of delta 1 and delta 2. So if we have this value for delta, then we have when the absolute value of x minus a is less than delta, the following two things must be true. The absolute value of f of x minus L is less than epsilon over 2, and the absolute value of f of x minus m is less than epsilon over 2. That's because we took delta to be the minimum. And so now we have all the tools we need to complete this proof, believe it or not. So from here we want to consider the absolute value of L minus m. And we want to show that this is 0, but we're going to show that it's 0 by showing that it is strictly less than an arbitrarily small epsilon. So from here we are just going to subtract f of x and add f of x on the inside of this inequality here. So this is going to equal L minus f of x plus f of x minus m. And now we are going to use our triangle inequality. So we know that the absolute value of L minus f of x plus f of x minus m is less than or equal to the absolute value of f of x minus L plus the absolute value of f of x minus m. And all I did for that L minus f of x is flip both signs, which is totally fine within the absolute value. And I hope that these two look familiar to you, because if you recall from our definition of the limit up here, we have that the absolute value of f of x minus L is less than epsilon over 2, and that the absolute value of f of x minus m is less than epsilon over 2. So knowing those two facts, that means we can write the following inequality. Well, we have that the absolute value of L minus m is less than or equal to the absolute value of f of x minus L plus the absolute value of f of x minus m, which is strictly less than epsilon over 2 plus epsilon over 2, which is equal to epsilon. But if we look at our extreme left and right hand sides, we have that the absolute value of L minus m is strictly less than epsilon, but if it is strictly less than something that is arbitrarily small, it must be equal to 0. And if the absolute value of L minus m is equal to 0, then that means that L is equal to m, and thus the limits of functions must be unique. Great, so let's get into our next proof of a theorem, which is our final proof for this video. All right, so our last proof for this video is going to be the proof of the squeeze theorem. So here's the setup for the squeeze theorem. We have L of x is less than or equal to f of x, which is less than or equal to u of x for all x in R. And then we have the following limits. We have that the limit as x goes to a of L of x is equal to L, which is equal to the limit as x goes to a of u of x, and we want to use that to show that the limit as x goes to a of f of x is equal to L. So let's start the proof. So we're going to suppose that we have the setup that we were given in this problem. We have that L of x is less than or equal to f of x, and which is less than or equal to u of x, and also our limit equality that we have written above. So, and the limit as x goes to a of L of x is equal to the limit as x goes to a of u of x, which is going to be defined as L. And so from here, we're going to use our strict definition of the limit. So let's use it on the limit of L of x first. So we have the limit as x goes to a of L of x is equal to L. Well, that's going to imply that for all epsilon greater than 0, there exists a, we'll call it delta 1 for this one, delta 1 greater than 0, such that we have the following: the absolute value of x minus a being less than delta 1 implies that the absolute value of L of x minus L is less than epsilon. And from here, we're going to break this absolute value of L of x minus L up into a compound inequality. So that will then imply that negative epsilon is strictly less than L of x minus L, which is strictly less than epsilon. And we're going to do exactly the same thing for our u of x. So I'll go ahead and write that out quickly for you, but it's exactly the same thing. Okay, great. So there I've used the limit definition just as I did above, and I've done the exact same manipulations there. So nothing too difficult there. So now we're going to use our inequalities. So we know that we have the following inequality holds, that L of x is less than or equal to f of x, which is less than or equal to u of x. And all we're going to do to this inequality is subtract L. So once we subtract L, we'll get that L of x minus L is less than or equal to f of x minus L, which is less than or equal to u of x minus L. And from here, we are going to choose our delta. So we're going to let delta equal the minimum of our two deltas, delta 1 and delta 2, that we used our precise definition of the limit to define above. So delta 1 and delta 2. And so we have when the absolute value of x minus a is less than delta, the following inequality holds. We have negative epsilon is less than L of x minus L, and that is from this part right here. And that is less than or equal to f of x minus L, which is less than or equal to u of x minus L, but that is strictly less than epsilon, and that is from right here. But now we can squeeze our epsilons around our f of x to get the following inequality. We have negative epsilon is less than f of x minus L, which is less than epsilon. But using the definition of the absolute value, we can write that as the absolute value of f of x minus L is strictly less than epsilon. But what does that mean? By the definition of the limit, that means that the limit as x goes to a of f of x must be equal to L. And that completes our proof. And now that we've proved the squeeze theorem, that's a good place to stop.